Hello, I am Sebastian Castillo, and this is my presentation on the Eggstronaut Lander. The objectives and design requirements of this project were as follow. To build a structure to prevent an egg from cracking from the height of a meter up, to help prepare us for the dynamics course next semester, to develop engineering communication skills. As well, the requirements were that the lander could not weigh more than 450 grams, it had to fit in 300 millimeter by 300 millimeter square, and the lander had to be made and out of commercial pasta and withstand a 1 meter drop. The materials were as follows: spaghetti, scissors, a hot glue gun, a ruler, a marker to mark the length of the spaghetti where I needed to cut, a cardboard box where I can hot glue my spaghetti joints together, chalk to measure out the square, and a tape measure so that way I can find where the meter was. I do apologize for this landing pad here. It is a little hard to see. It was kind of dark out when I started to take this picture, and the color did not help out at all. To find the velocity and the forces produced, I used the following equations. For velocity, I used velocity final squared is equal to velocity initial squared plus 2 times acceleration constant squared, 2 times acceleration constant times initial position minus final position. Here you can further see when the items are plugged in that it was equal to that v squared was equal to 0 plus 2 times 9.81 times 1 minus 0, which then produced an answer of 4.43 meters a second. Now, for the equation to find the forces produced, I had to use the conservation of energy, the law of conservation of energy. T1 plus V1 is equal to T2 plus V2. Here, T is equal to kinetic energy, V is equal to potential energy. The equation for kinetic energy is as follows: 1/2 mass times velocity squared, and potential energy is mass times gravity times height. Here, I got my mass by combining 3 large eggs together and finding the average mass, which came out to 58.66 repeating grams. My velocity, as stated previously, was 4.43 meters a second. Gravity is 9.81 meters a second squared, and the height was 1 meter. To find kinetic energy, I did 1/2 times 58.66 times 4.43 squared, and that gave me a total of 575 joules. For potential energy, I multiplied 58.66 by 9.81 by 1, which then also produced 575 joules. Quick note, 1 joule is equal to 1 Newton. How would I design this lander? Simply, the legs would be spread out far. The legs would also have to be pyramidal in shape. The egg container would have to allow for extra space for cushion, and trusses would have to be employed everywhere in the body. Brainstorming. For some quick research, I just simply Googled Mars lander. From there, I was able to see the pictures of what the lander looked like. 3 designs I produced were all derivative of one another. I made the calculations for each, and I decided to go with the one on the very top. That one I like to call the Mars lander because that is the one that kind of represents the lander the most. The other 2 I like to refer to them as the extended bottoms. Some advantages to the extended bottoms were that for one of them it was easier to solve as it had strictly 45-degree angles, which made it easier. Additionally, it had more material to cushion the fall, so it would absorb more of the energy instead of just transferring it straight to the egg. However, these designs were not as strong as my Mars lander, one that I like to call. The prototype that was most similar to the Mars lander was the strongest one, but it was pretty difficult to build as well. And also, it did not provide as much cushion as the legs met with just the lander right there, and that was all there that was stopping it from absorbing from not it absorbing too much um, energy. The final design, as I said, was the one that I chose that most represented the Mars lander. The dimensions of the box where the egg is being contained measured 8 centimeters by 8 centimeters by 10 centimeters. The dimensions of the lander where the legs meet each other was 28 centimeters by 28 centimeters by 10 centimeters. The lander's mass weighed in at 21.34 grams. Originally, the box was going to be a lot more solid, though this was a lot more time consuming and trusses allowed for more structural soundness. Additionally, there was a harness implemented around the egg to secure the egg in place. The calculations of the lander leg in the joint C, the side view. For here, I used the equations of equilibrium, where the summations of F is equal to 0. For the summations of the force in the Y, I used summation of Fy is equal to 0, which is equal to 575 newtons cosine of 20 minus the force in CB times the sine of 25 degrees. The force in CB came out to 1,279 newtons. Then to find all the forces in the X, I used the summation of forces in X is equal to 0, which is equal to negative force CA plus 1,279 newtons cosine 25 degrees minus 575 newtons times the sine of 20 degrees. And the forces in the CA came out to 963 newtons. The calculations of the lander and leg joint A, again, I use the same equations of equilibrium. Here in the forces of Y, I use the summation of forces of Y is equal to 0, which is equal to force in the AB minus 963 newtons times the sine of 20. And force AB came out to be 329 newtons. Calculations of the lander leg joint B top view. I use the same equations of equilibrium. Here, so the summation of force in the X is equal to 0, which is equal to 575 newtons times force in the BC sine 69.9 degrees. The force in the BC came out to be 612 newtons. For the force in the Fy, I used summation of force Fy is equal to 0, which is equal to 612 newtons cosine of 69.9 degrees minus the force in BA. Force in BA came out to 210 newtons. Calculations of lander leg joint C, top view. Here I use the summation of forces in the X, where summation of forces in the X is equal to 0, which is equal to negative F in the CA plus 612 newtons times the cosine of 21.1 degrees. 20.1 degrees, pardon me. FCA came out to be 575 newtons. This is a visual representation of the work that I've done. The performance. Here I have two tables describing the lander. The first table is the weight of the lander. The weight of the lander with the egg came out to 80 grams. The weight of the lander without the egg came out to 21.34 grams. The second table is the results. Here you can see when I dropped it at a height of a meter, the result unfortunately was the egg cracked. Then this next slide will show the visual representation of the performance.
It's recording.
It broke. Conclusion. Some objectives were achieved. For example, I was able to create a lander made out of pasta using glue in only the joints. I was able to drop the egg from a height of a meter, though unfortunately it did crack. I was able to solve all the equations necessary, as well as being able to prepare myself for the dynamics course a little bit by being able to use the equation of velocity and the law of conservation of energy rather easily. Some of the lessons I learned were I solidified my understanding of the method of joints and sections, as well as my understanding in the moments and my understanding of the equations of equilibrium. Additionally, I was able to solve for velocity and to find kinetic and potential energy. As far as redesigning my lander, I would redesign it in two ways. I would make the legs longer so that way it would meet the ground quicker than the body would. Additionally, I would add a lot more trusses to the body where I did not have as much trusses as I felt like I could have had. Additionally, I would have used more pasta than instead of just one strand for each joint member. Thank you for listening to my presentation.